Vodcast number 1. Hope you have your notes outlined out and you're ready to go. All right, let's review a little bit from what we talked about in Chapter 5. We talked about chemical thermodynamics and how they're concerned with energy relationships and chemical reactions. We talked a lot about energy, but we also talked about work and how work and energy together, heat energy, made up all of the internal energy. So what drives a chemical reaction to happen? If you remember from last year when we did thermodynamics, you might remember that things wanted to have low entropy, low energy, and high disorder. It wants to get itself in a thermodynamically stable position by spreading out and releasing as much energy as possible. That has to do with enthalpy and entropy, which we're going to review in this chapter and their relationship to each other. So the first law of thermodynamics relates to those. It says that the energy that can be transformed, changed from one form to another, but cannot be created or destroyed. So all of that energy has to be able to be accounted for. Q as the enthalpy and W as work are the two components that comprise the total energy change of a system. All right, so we're going to be talking first about what it means to be spontaneous. And in chemistry, that means anything that can proceed without outside intervention. So let's look at these pictures here. You've got a couple eggs. When you drop them, they break. That's spontaneous. But it is not spontaneous for them to go from broken eggs back up into your hand as whole eggs. Not spontaneous. Here's a little more scientific kind of example. If you've got a gas at 1 atmosphere in this container and a closed spigot and another empty flask, if you open that spigot, the gas is going to spread out amongst those two containers. That is spontaneous. It would not be spontaneous for it to go in the other direction and have all the gas particles in one container. Could a reaction be spontaneous in both directions? What do you think? Well, you've got a nail rusting here, spontaneous, not spontaneous to go back the other way. So let's talk about that a little bit more. So here's an example of some situations. Let's think about these. It's example 19, exercise 19.1 from your text. First, if you put a piece of hot metal, 150 degrees, added to 40-degree water, the water is going to get hotter. Heat is going to transfer from high energy to low energy. It's going to warm that water up. Write down whether you think that's spontaneous or non-spontaneous. B, water at room temperature decomposes into hydrogen and oxygen gas. Spontaneous or non-spontaneous? Finally, benzene vapor is at standard atmospheric pressure and it condenses to liquid benzene at a normal boiling point, at its normal boiling point of 80.1 degrees Celsius. Spontaneous or not spontaneous? All right, let's look these over. A, I hope you said that is spontaneous because it would indeed transfer the heat from the hot metal to the water until the temperatures are isothermal, the same. So that one is spontaneous. B, water decomposing. Now you may have seen this happen in lab last year where you take electricity and you can break water into its components, but you will never see water do that on its own. And so therefore it is non-spontaneous. You have to put energy in to make that happen, and it will never, ever, ever happen on its own. So finally, benzene vapor at its boiling point at atmospheric pressure will indeed condense at its boiling point, but it will also boil at its boiling point. So it will be condensing and that evaporating at the same time, at the same rate. It will be at equilibrium, which by definition is not spontaneous or not spontaneous. When something's in equilibrium, then it is not considered to be one of those that drives itself one direction or the other. So the question is, can something be spontaneous in no direction? In both directions? The answer is no. Okay, so a change in temperature can change the spontaneity of a change. You can have one thing that is spontaneous at one temperature, but non-spontaneous at another. For instance, ice melting. If you're above the freezing point of water, 0, it will be spontaneous for the ice to melt. But if you're below 0, the reverse process is spontaneous, so it will freeze, not melt. So it's important to take temperature into account. Temperature affects spontaneity. And let's look at what's reversible and what's not reversible and talk about that a little bit. So a reversible process is when a system changes so that the system and surroundings can be returned to the original state by exactly reversing the process. So, for instance, if you have something hot inside something slightly cooler and it's completely insulated, it will transfer the heat, and then that heat will transfer back. It will go back and forth until it gets to one temperature, and that would be reversible. It's kind of an idealized situation. It's hard to have anything that's purely reversible. But an irreversible process cannot be undone. And so something truly spontaneous is irreversible. So like that gas we talked about, if you take a gas at a certain pressure and allow it to spread out into more volume, you will not be able to get it all back into that one pressure, that one section, without inputting work and making it go back. All right, second law of thermodynamics. Definition: a thermodynamic quantity measuring the randomness in a system. Okay, that looks like one of my professor's offices from grad school. Entropy. Now you can quantitatively measure entropy, although it's not easy to do and something that we usually just look up. Quantitatively, the more disordered or random a system, the larger the value of S, the entropy value. Like total energy, E, and enthalpy, entropy is a state function, which means that a change in S is simply S final minus S initial. So consider melting ice. Is the entropy increasing or decreasing? If you've got it in a crystalline state and you start in the solid, you're going to increase entropy as it melts because it's going to get more disordered, more possible movements of the water molecule. So for a process occurring at a constant temperature, when you're talking about something at a phase change, you can measure that change. So delta S is the amount of energy it takes in terms of enthalpy, the heat, and divide it by that temperature. So you could measure entropy change at a phase change. For example, exercise number 19.2. If you have mercury at room temperature and you get it to its freezing point, its molar enthalpy is delta H is negative 2.29 kilojoules for every mole of mercury. So that is how much Q it would take to freeze a mole of mercury. If you wanted to melt a mole of mercury, you would have to put in a positive 2.29 kilojoules for every mole. So I want to know, what's the entropy change for what's the entropy change of the system when 50 grams of mercury freezes? So pause and calculate your moles and kilojoules, and then kilojoules per Kelvin for that change. you should get negative 2.45 joules per Kelvin. So if you are freezing, you've got a negative 2.29 kilojoules for 1 mole, multiply it by the number of moles of mercury, and then divide it by the freezing point in Kelvin. Don't forget to do it in Kelvin. All right, here's some more. Now this is a little more theory about what entropy is really describing in terms of the molecules. The entropy of the universe increases for spontaneous processes. It's always going to be true in the universe. But the entropy of the universe does not change for reversible processes. So, for reversible processes, the net change in disorder is 0. But for irreversible processes, it increases. So anything that's spontaneous, combustion, melting above melting points, etc., is going to increase the disorder in the universe and cause things to be more spread out and more thermodynamically stable. For instance, if you've got a salt like this KCl dissolving in water, you can see how it's in a very stable state as a solid, and then the water pulls it apart and spreads it out more, giving it more disorder. All right, a man named Ludwig Boltzmann described this at a molecular level. So he talked about that randomness as being caused by the possible motions of a molecule. And it's not only they can move translationally, they can move from one place to another, the entire molecule, but the molecules itself can vibrate within the molecule. The bonds can expand and contract. They can sort of wag and twist. It's like the molecules are dancing. And that's one way that you get more possible disorder in a molecule, is not only by its movement, but also by its motion. So that has some consequences for what we call increased entropy. So he referred to the motions as the molecule's microstates. So every possible different motion something has is a microstate. Now, this equation I'm going to show you from Boltzmann does not show up on the exam. It's just sort of there for the cool stuff in physical chemistry. So if each thermodynamic state has a specific number of microstates, and that's something we're not going to get into how you might count them, but they all have a W, then entropy is K, which is a constant, times the natural log of that number of microstates. Pretty simple relationship. And Boltzmann's constant is this really small number, 1.38 times 10 to the negative third joules per Kelvin. So any change is going to be the change of the final state minus the initial state, and you can rewrite it this way. So therefore, entropy increases with the number of microstates. If you had the same number of microstates, it would be natural log of 1, which would be 0, and the change in entropy would be 0. But if W is any number greater than the initial, then you'll have a positive change in entropy. All right. The number of microstates and therefore the entropy tends to increase with temperature. Obviously, there's more translational motion and more energy in the particles. Volume, because you have more space for the molecules to move around in and therefore can have more freedom of motion. And the number of independently moving particles. So if you have a reaction happening and you go from 2 particles to 3 or more, then you've got more microstates. All right, so let's think about these examples. Predict whether the entropy is a positive or negative change. Water freezing, ions precipitating into a precipitate, iron rusting, and nitrogen and oxygen reacting to form nitrogen monoxide. All right, water freezing. That will go from a liquid to a solid, which is going to be a negative state change of entropy. It's going to have less freedom of motion. Ions to a solid, again, a negative delta S. Iron rusting, you've got solid iron, oxygen gas into one compound. That's going to be, because you've got a gas that's becoming part of a solid, that is also going to be negative. And nitrogen gas and oxygen gas, N2 plus O2 to yield NO. You've got 2 molecules changing to 2 molecules. There is no measurable change of entropy in that system. All right, one last change. Choose a sample of matter that has greater entropy in each pair, solid sodium chloride or a mole of HCl gas. The gas will have more freedom of motion. 2 moles of HCl gas or 1 mole of HCl gas at room temperature, both at room temperature. Obviously, the 2 moles, you've got more particles, more possible motions. 1 mole of HCl gas and 1 mole of argon, that's going to be the HCl gas because it's got a bond and it'll have more vibrations, etc., than an individual particle. Okay, lastly, third law of thermodynamics says that the entropy of a pure crystalline substance at absolute zero is 0. So the only way to have 0 entropy is to be at absolute 0, where there's absolutely no motion. That's where we're going to end today. We'll talk about the entropy change in chemical reactions next time. Please fill out your summary form and have a good night.